So what we're going to talk about now is we're going to talk about differentiability and this thing called the error function. And so the reason why it's important to talk about differentiability is because sometimes some functions are not necessarily differentiable at particular points, right? And we've got to take those into account. So if you remember from single variable calculus, we had these two instances, or we have, here's two examples. One is when a function is discontinuous at a particular point. Or two, we also have this idea of a sawtooth function. So like, for example, we imagine we want to find what the derivative is at x equals 0, right? But what we have is we actually have, say, an asymptote there, right? And so in this case, it's not going to be differentiable there, right? We're not going to be actually able to tell what the value of the derivative is. Or the sawtooth function, if you remember, the sawtooth function has a corner, or has corners, okay? And when it has corners, right, at these points, wherever those corners are, wherever the sawtooth is, right, you also have not differentiable, right? Continuous, but not differentiable. So like discontinuity, that's one problem. You also have these sawtooths or corners. And then also, if you remember, we also had these cusps, right? So cusps ended up being an issue. And that was basically that the derivative was different if you were coming from the left or if you were coming from a right. And so that's a problem. And what we are looking at now is we're looking at what are the issues that we have, or how do we know that we actually can find partials, that we do have a differentiable function based upon, and what are the criteria for a function being differentiable. So here's a definition for us. It's a definition of differentiability. So a function f of xy is differentiable at the point p of x naught, y naught. So at a point, if for all points xy in a disk around p, so now in a region around p, and we did the same thing when we were proving differentiability, we just had it in an open interval, we can write f of xyz equals, basically we can find a tangent plane, right? There's a tangent plane plus this thing e of xy. And e of xy is defined, okay, is our error term. Okay, and we need to make sure that that error term it becomes 0 as xy approaches whatever our point is. So basically what we want to have happen is we want to have this function, okay, all right, actually become, or the value that we get for this function actually become the value for the function as our point xy approaches x naught, y naught. Right? So as we get close to whatever function that we're looking for, or that we're trying to find the derivative of, okay, on our surface, right, on our tangent plane, we're like closing in, and as we close in, that error term should actually move to 0. All right, so let's actually look at this error function and figure out how we might actually be able to use it, or how it is that we use it in order to prove differentiability. So if you remember, we have this function, or this equation, f of xyz is going to equal the tangent plane, okay, so there's our tangent plane, plus some kind of error. So let's actually look at this and see an example to kind of show how it is that we're going to go out and find e of xy, and then we're going to prove differentiability using that e of xy, right? So we got to figure out what it is. So the first thing that I need the tangent plane. For, in this case, we're going to use f of xy equals 2x squared minus 4y. And we're going to prove that it's differentiable at 2, negative 3. So I'm going to first need f of 2, negative 3. And that's going to equal 2 times 2 squared minus 4 times negative 3. And that ends up being 8 plus 12, so that ends up being 20. Then I'm going to need fx. fx is going to end up being 4x. And so fx at 2, negative 3 will end up equaling 4 times 2, which equals 8. And I'm going to need fy. Fy is then going to be just negative 4, all right? So it's constant, right, because the y part is linear, so we don't need to do anything else with that. So fy is just negative 4. So consequently, we're going to get our tangent plane is going to end up being 20 plus 8 times x minus, and so our x minus 2 plus negative 4, or rather minus 4 times y minus a negative 3, so y plus 3, right? And here's your x naught, y naught. Okay? And that's the tangent plane for f of x, y, z. Okay? So now I'm actually going to simplify this. I'm going to make this 20 plus 8x minus 16 minus 4y minus 12. And so this ends up being 8x minus 4y minus 8. So now I'm going to plug that into here. Okay? And I know, so that's my tangent plane. So that's going to be 8x minus 4y minus 8. And on the other side, and then plus, by the way, e of xy. And on the other side, what I'm going to do is I'm going to set that equal to then 2x squared minus 4y. So I got 2x squared minus 4y. And in order to find e of xy, what I'm going to do is I'm just going to simplify. So I'll subtract 8x, add 4y, add 8. And so I get now 2x squared minus 8x plus 8 is what's going to be e of xy. That's my e of xy. So simple process there. We're going to go in, find the tangent plane. Okay, and then once I find the tangent plane, I'm going to basically plug it into this equation here that I have to satisfy for differentiability. And that will then help me to find what e of xy is. Okay, so now I have e of xy. That's finding e of xy. Now remember, we'll scroll back up for just a second. In my differentiability, I have to have e of xy divided by, and this distance function of the distance from x and y, and we're going to have that limit. The limit as this approaches 0, as xy approaches, in this case 2, negative 3, has to end up equaling 0. So let's see what we get. All right, so I got the limit as xy approaches, and x naught, y naught is 2, negative 3. It'll be e of xy, so e of xy divided by the square root of x minus 2 squared plus y plus 3 squared. Because that's x naught, that's y naught. And this is then going to be the limit as xy approaches 2, negative 3. And e of xy is going to be then 2x squared minus 8x plus 8 divided by the square root of x minus 2 squared plus y plus 3 squared. Okay? And there we go. So we're looking for a limit, right? If you remember with our limits, let's say, for example, let's see if we can do some algebra here. Okay? If we look here, this is going to end up being 2 times, so this is the limit, and we'll have xy approach 2, negative 3. 2 times x squared minus 4x plus 4 all over the square root of x minus 2 squared plus y plus 3 squared. And this is then going to be the limit xy approaches 2, negative 3 of 2 times x minus 2 squared divided by the square root of x minus 2 squared plus y plus 3 squared. Now what I'm going to do is I'm going to use a little trick, or not really a little trick. What I'm going to do now is I'm going to say this is going to be less than or equal to, and it'll be the limit xy approaches 2, negative 3, and this is going to end up being, if we look at this, this is x minus 2 squared, and that should actually be, it's going to be less than or equal to x minus 2 squared plus y plus 3 squared. Okay, all divided by the square root of x minus 2 squared plus y plus 3 squared. Okay, or actually 2 times this, 2 times this, 2 times that value. And the reason why is this. X minus 2 squared, that's just what I have right here. Y plus 3 squared has got to be greater than or equal to 0. So consequently, we're going to add a positive part to our already remaining value. So consequently, we're going to get this as being less than or equal to. And the reason why we did this is because this is going to then let it equal to the limit as xy approaches to negative 3, okay? And this is what we can just factor out a square root. So this is going to be then the square root, or 2 times the square root x minus 2 squared plus y plus 3 squared, okay? And now I can just substitute. Substituting in 2 in for x and negative 3 in for y, this just ends up equaling 0 by substitution. It's kind of like squeeze theorem in some ways, like how we ended up doing this, this limit. The limit, right, okay, it just requires us to kind of think through and say, okay, well, is there some way for me to actually get rid of the square root of x minus 2 squared plus y plus 3 squared? And this is actually one way we can go about doing it. Notice now it actually ends up equaling 0, exactly 0, by algebra. So we don't have to check paths, we don't have to do anything with it. We have shown here that e of xy, okay, over the square root of x minus 2 squared plus y plus 3 squared ends up equaling 0, okay? So f of xy is differentiable at 2, negative 3. We've shown that it in fact is differentiable there, okay? So let's just go through the process and talk about the process real quick here. So what I needed to do was I needed to find the tangent plane. Okay, so I went in and I found the tangent plane, all right? And once I did that, then I could plug in the tangent plane into my equation, right? This is what happened right here. I have f of xyz, okay? And that'll equal, or f of xy, and that'll equal my tangent plane plus e of xy. A little bit of algebra will then give me what e of xy is. Okay, and I should actually rewrite this as f of xy. Okay, and now that I've got e of xy, what I'm going to do is I'm going to take the limit as xy approaches whatever value that I'm actually looking for. In this case, 2, negative 3. That's the point I'm looking for differentiability at. And I'll take e of xy, that function, divided by the distance quotient, or the distance formula from 2, 3. A little bit of algebra, a little bit of cleverness in order to find my limit, and I get that limit actually equals exactly 0. Since it actually equals 0 as xy approaches whatever x naught, y naught is, we can say that f of xy is differentiable at that point. And that actually gives me my answer. Let's try another one. Let's take a look at another problem here. Let's show that f of xy equal to 3x minus 4y squared will be differentiable at the point negative 1, 2. Okay? So remember, first thing that we want to do is find the tangent plane. So we're going to first find the tangent plane. And so that'll end up giving me first f of negative 1, 2 equals 3 times negative 1 minus 4 times 2 squared. So that's negative 3 minus 16, so it's negative 19. Okay. Next up, we got fx. fx is equal to 3, right? That's it. And fy will end up equaling negative 8y. So fy at negative 1, 2 will equal negative 8 times 2, which equals negative 16. So what we get here is we're going to get our plane, our tangent plane is going to be z equals, okay, z equals 3 times x plus 1, right, because negative 1, 2, x plus 1 plus, or minus rather, 16 times y minus 2 minus 19. And so that's 3x plus 3 minus 16y plus 32 minus 19 equals, again, 3x minus 16y, and this is going to end up being plus 16. And there's our tangent plane. Next up, we're going to set f of xy, f of xy equal to our tangent plane. So f of xy, which equals, in our case, 3x minus 4y squared. And then we'll set that equal to 3x minus 16y plus 16 plus e of xy. And now let's go out and we'll figure out what these are. So we'll subtract 3x from both sides. Okay, we end up with negative 4y squared minus 16y, or plus 16y minus 16. That equals e of xy. Considering that I saw that I needed to factor it earlier, I'm probably going to do that again. I got negative 4 times y squared minus 4y plus 4. Well, that makes life easy. And that ends up being negative 4 times y minus 2 squared. So that's my e of xy. Now I've got to prove the limit as xy approaches, and this is negative 1, 2. Yep, negative 1, 2. We'll take e of xy, so that's negative 4 over y minus 2 squared divided by the square root of, in this case, we'll have x plus 1 squared plus y minus 2 squared. Okay. Great. So there we go. And now we're kind of going to do a pretty similar trick as to what we did earlier. It's a little bit different given the fact that we have a negative 4 right here and not a 2. But what I can actually do is I can just say, well, forget the negative 4. If I take negative 4 times y minus 2 squared, that's negative. All right? Not going to work. Instead, let's just choose, we'll add 2 positive values here. So we know that this is going to be then less than or equal to the limit as xy approaches negative 1, 2. And let's choose the right 2 values to add together. How about y minus 2 squared plus x plus 1 squared? All divided by now the square root of x plus 1 squared plus y minus 2 squared. All right, so let's pause for a second to see why this makes some sense. Y minus 2 is positive. Okay? Y minus 2 is positive. Negative 4 is negative. We multiply a negative number times a positive number. Okay? We get a negative number. At the bottom, down at the bottom, that's a positive number because both of the values are squared and we're adding them together. Okay? So this is positive. So we have a negative divided by a positive. Okay? Well, the limit as xy approaches negative 1, 2, then is going to be, it is going to be, in fact, less than or equal to. This whole thing will be less than or equal to whatever we get for this. Okay? And the reason why is because this now is positive. Right? It's 2 positive numbers added together, divided by another positive number. That's positive on the bottom. So this is now positive. Okay? So its limit should be that, like, yeah, there it is. The limit should be less than. So what we're going to see, you're going to see now is like, okay, well, this is what happens then. We get the limit, xy approaches negative 1, 2, and now what we're going to get is we got y minus 2 squared, okay, plus x plus 1 squared, okay, but now square root because we're dividing through by the square root. Plug in the values for negative 1 and 2, and we get 0 by substitution, and we're done. So thus, f of xy is differentiable at negative 1, 2. There we go. So now we have some helpful theorems for proving differentiability or thinking about differentiability. One is that differentiability is going to imply continuity. That's theorem 4.6, or for us, theorem 4.6, whatever that means. And so that is if we have f of xy is a function of 2 variables with x naught, y naught in the domain of f. If f of xy is differentiable at x naught, y naught, then f of xy is continuous at x naught, y naught. Well, what that means for us actually is that means that if we have a function that is not continuous, then that function is also not differentiable. That's called the contrapositive. So the contrapositive is this. So this statement is that if the function is differentiable, then it's continuous. The contrapositive of this is if f is not continuous, then f is not differentiable. So if we know that we have a function that is not continuous at a particular point, then we also know that that function is also not differentiable at that point. That equates to what we saw with calculus and single variable. The second theorem that we have here is continuity of first partials implies differentiability. And both of these, by the way, we're not going to be proving here because they actually are kind of complicated. It's beyond the scope of the class. But this is saying, like, let z equal f of xy be a function of two variables with x naught, y naught in the domain of f. If f of xy, fx xy, and fy xy all exist in the neighborhood of x naught, y naught, so that's basically around those values, and are continuous at x naught, y naught, then f of xy is differentiable there. Okay? So in this case, this actually might be an easier thing for us to do, is to actually go in and show that if one of the partials is not differentiable, not continuous, then the whole function is not differentiable. So let's take a look at an example. So we've got an example here, all right? And let's have it, and we've seen this before. We know actually that this is that this function is actually not continuous. It's got, or it doesn't have a limit at a particular point. So x squared plus y squared when xy does not equal 0, 0. And we have 0 if xy equals 0, 0. So we already know that that limit actually doesn't exist. We've proven this one before. Okay? We've done this before. But let's actually look at this and see, right? We want to prove that f is not differentiable at 0, 0. So it's not differentiable at 0, 0, a place where it's got a hole. Okay? So what we'll do first is we're actually going to figure out df dx. Okay? Find df dx, right? And that's going to end up equaling, well, we'll take the derivative with respect to y, or excuse me, derivative with respect to x, so that's x times the square root of x squared plus y squared minus, and then this is, we'll take the derivative of x squared plus y squared, so this is going to be the square root of x squared plus y squared, okay, to the, or excuse me, it's going to be x squared plus y squared, okay, to the negative 1/2 times 1/2 times 2x, all divided through by the square root of x squared plus y squared squared. We go in and we do a little bit of housekeeping. What we'll get is we'll get that df dx here in this case is going to equal y cubed over x squared plus y squared to the 3/2. Okay? So we'll go in and we'll get that that's the case. And what we want to know is that if, okay, f is differentiable at 0, 0, then fx is continuous at 0, 0. Okay? So if f is not continuous, so if fx is not continuous at 0, 0, then f is not differentiable. So what we know, we already know that fx at 0, 0, okay, we're actually given a value there. We want to actually find the limit as xy approaches 0, 0 of fx at xy, okay? And the reason why we want to do this is because we need, this is the condition for continuity. So it's a condition for continuity. If it doesn't hold, if that limit does not exist, then we have a non-continuous function, okay? And then if it's not continuous, then f is not differentiable. So we go in here and we see, all right, this is the limit as xy approaches 0, 0 of y cubed over x squared plus y squared to the 3/2. And if we first we're going to have the limit, and we've actually seen this before, we'll come in from x equals 0, or actually let's come in from y equals 0, okay? We come in from y equals 0, and we get x 0, all right, to 0, 0. This ends up being 0 over x squared to the 3/2, and that just equals 0. So that's the function, or that's the limit when we come in from the path y equals 0. Then we'll consider, let's say y equals 2x, or actually, excuse me, x equals 2y. All right, we're going to consider x equals 2y. All right, and so we'll plug that in now. And so we're going to get the limit xy, or excuse me, 2y going to 0, 0. And this will be y cubed over 2y squared plus y squared to the 3/2. And this will then equal the limit, all right, and we'll just consider this, we'll call this a variable, we'll call this variable t. T goes to 0, all right, of, oh no, I want you to write 2y to 0, 0. And this will be y cubed over, this is 4y squared plus y squared, so that's 5y squared to the 3/2, okay? And this ends up equaling then the limit 2y going to 0, 0, y cubed over 5y cubed, which equals 1/5, right? The y cubes cancel, it becomes 1/5. So it equals 1/5 when we're coming from the path x equals 2y, and it equals 0 when we come from y equals 0. All right? The limits are not equal on two different paths, so the function is not differentiable. All right? It's important. So basically, so actually the functions are not equal on two different paths. Fx is not continuous at 0, 0. So the function is not differentiable at 0, 0. And we should actually just complete that. Okay? So what we see here, all right, is the fact that what we showed is that one of the partials, fx, was not in fact continuous at a particular point in the domain, okay, or at the particular point that we're looking for differentiability. And since it wasn't continuous, we get not differentiable, right? Key point to remember. So here's the big remember thing here for us. Remember, right, continuity does not imply differentiability. We can have things with corners, for example, right? So we can have continuous functions that are not differentiable, but differentiability does imply continuity. It's a logic idea. And so, not continuous implies not differentiable. All right? Don't get them twisted, right? Continuity, you can have a continuous function that is not differentiable, but you cannot have a differentiable function that is not continuous. Consequently, if your function is not continuous, then your function is not differentiable. And that's what these last two theorems actually tell us. It also tells us if fx not continuous, that implies not differentiable. And if y not continuous, the whole function, right, is not differentiable. And this is at x naught, y naught. All right? So that actually ends our conversation on differentiability. So to summarize differentiability, 1, we actually have a definition for differentiability. It's shown earlier on inside of this video, in which what we have to do is we actually have to set the function equal to the tangent plane plus some error, right? And that show that that error divided by our distance quotient, or our distance function, excuse me, it ends up equaling 0 as we get the limit xy approaches whatever point that we're looking to approach to be differentiable, right? So that's the first one, and that actually, in simple cases, we could actually prove differentiability there. On the other hand, proving something is not differentiable, One of the best ways to go about doing that is actually to show that the function is not continuous at that particular point, or to show that the partials, fx or fy, you might have to do both, might have to do one at a time, are not continuous at that particular point, and hence are not differentiable. Okay? Because if a function is differentiable, then the function is continuous at that point, and its partials are the function is continuous at that point, and its partials are continuous at that point. So consequently, if we think about this from the contrapositive, which is like flip it and negate it, if the function is not continuous, or if its partials are not continuous at that point, then the function is also not differentiable at that point. Okay? And so these are some like big ideas, big mathematical ideas that show us, when can we determine that we can actually like take the derivative of a function at a particular point.